Hey there, everybody. Back again. Here we are together. Um, so, we're going to start looking at coordinate transformations. That is from, you're probably used to hearing polar coordinates from vector calculus. So, polar coordinates, that would be our latitude, longitude, and some radius. And we're going to transform those to Cartesian coordinates, so x, y, and z. But before we get into that, just as a segue from the last session we were together, we introduced very briefly the topic of convergence. And I'm going to build on that just a little bit more here. I'm not going to get fully into the concept, but I want to expand on it just a little bit so that when we do talk about it, we are somewhat in familiar territory. We've seen how it works, right? So what we discovered from last time is if we have 2 points, there's Klamath Falls in Oregon and Missoula, Montana, and a lot of these, I'm going to exaggerate the angles and the lines in order to make the point. When we calculated, so we know that on a plane, right, that the azimuth we can calculate as long as we are actually working on a piece of paper or a digital screen, that azimuth would remain constant. This is the azimuth. Well, I'd need a north. So there's our north axis. And we would find that on the plane, this angle, the azimuth, and on a plane we use alpha for azimuth, it remains constant on the plane, right? Which would imply that that when we got to Missoula, Montana, we would be on that same azimuth, and then we could just add 180 degrees and get our back azimuth. But because of the distance, we started experiencing the idea that the azimuth changes with the distance. So really what's happening, if I can erase these, is if I were to represent this in a spherical manner, I'll use yellow for the spherical course. You've seen on like flight paths how the line between 2 points looks curved when we look at it on a piece of paper, right? Or like that. Well, what's going on with convergence, or with what we were experiencing, is that at Klamath Falls, exactly at that point, if we were to draw a tangent, then that is the azimuth that we're originally setting out. But by the time we got up to Missoula, Montana, we had an azimuth that if we were to take the back azimuth, it would be something. So here's our north. Let's see, I'll draw a north here too. So there's our north axis at Missoula, Montana. What we find is that, and this is a cartoony representation, that the azimuth is actually greater than 180 degrees. And what we're experiencing is along this curve, our azimuth would follow the tangent until we got to Missoula, Montana. That is convergence of meridians, or the effect of convergence of meridians. And in fact, the number that we calculated, our forward azimuth when we're at Klamath Falls, was different than our back azimuth by more than 5 degrees. If we're trying to pilot a ship and we're following a constant bearing, that's going to be a real problem because we're going to miss our mark and maybe even be out in the ocean somewhere without supplies. So when navigating ships back in the day, when they were using sextants and compasses, and if they didn't correct for that convergence, they could be in real trouble. So convergence is an important concept, and we use it in cartography quite a bit. So why do we even use planar representations of azimuths? Well, for most survey projects, we're working on projects where distances are less than a mile. So convergence really isn't going to show up. We're definitely working with margins of error that supersede convergence. So I guess what I mean by that is within our margin, whatever convergence we experience on short distances, and I would even say less than 30 miles, the amount of it's not error, but I'll call it error, that convergence would contribute would be less than the errors we would expect just from our setups, from random errors. So we need to consider convergence in highway projects or projects where accuracy and precision have small enough margins of error, acceptable margins of error, that convergence would play a part. And those could be long distances or just super high precision projects. So now, just in brief, we're going to expand on the topic of convergence of meridians. And it's not going to take very long. I'm just going to take a few minutes to talk about what this is. So convergence of meridians. And we just say convergence for short. We don't say convergence of meridians every time. Now, on a globe, we know that the lines of longitude are kind of, if we're to face them from a certain perspective, we have these, this is our globe. And we notice that the lines of longitude converge at the North Pole. That is convergence. And it has an effect on the work that we do. I'm trying to erase that. So in short, I'll define convergence. This is very short. This isn't an official definition, but in short, convergence, and I'll just write convergence, but convergence of meridians is the difference, or they'll say the angular difference, that's an A, angular difference between grid north, or north on a plane, and geodetic north, or north on a sphere, along a line of longitude, a meridian of longitude. That difference is convergence. Let's see. Yeah. In short, convergence is the angular difference between grid north and geodetic north. So if I had a point, and depending on where that point is oriented on a specific map projection, and I can draw north from that point, that's grid north. But geodetic north would actually be this curved line, and the azimuth, and we could draw a tangent there, right? So that's tangent to that curve. This angle is known as convergence. We usually call convergence gamma. So gamma is convergence of meridians. And no matter what path we're taking, unless it's due north along a meridian, is going to suffer from, I say suffer, it's going to experience problems due to convergence. And convergence is different at each point along our course. So what that looks like, move this up, is if I have this course, and we'll just make it a simple horizontal course. So I'm following this course along, let's say I'm going along a parallel. Doesn't really matter that I'm going along a parallel, but I'm moving this way. And I have these check-in points. So here I'm moving along, and then I'm there, and then I'm there, and then I'm there, and then I'm there. And at each of these points, there is a grid north, right? Now, these are supposed to be vertical lines, but doing my best. So here's grid north, and that's what we like to see on a map, right? We don't like to see curved lines on a map. We like to see north as a grid. And then what we're experiencing on the globe, however, on a sphere, is that there's these curved lines that are pointing up to the North Pole. Now, let's say that, imagine looking at a globe such that one of the lines of longitude appears perfectly vertical, right? That is because as we turn the globe, those lines of longitude, as they become head-on, face-to-face with our perspective, they more closely match with grid north, or I should say, grid north more closely matches with geodetic north. So if we have some position over here on our projection where grid north actually perfectly aligns with our meridian, then as we get closer, these geodetic lines start becoming less curved until we're here. But then as we move easterly from that central meridian, is what we call it in map projections, then convergence starts going the other way, right? So, and not only does it start going the other way, but it starts going the way more drastically, right? Oh, it's supposed to be the other color. So that is convergence of meridian. As we get closer to our central meridian, whatever meridian that might be, and in map projections, we purposely pick our central meridian to accommodate our specific project area. So this meridian that aligns with grid north can be any meridian we want, but we're going to experience convergence on either side of that central meridian, right? So we'll just get, so these white lines are grid north. And here's our course, which in this case is along a parallel of latitude, just for simplicity. And we're moving that direction. And these lines then are geodetic north. And where the geodetic north aligns perfectly with grid north, that's called the prime meridian. Okay? And And we'll discover in map projections that any attempt to impose straight lines onto a sphere results in convergence. Okay. I think that's as far. Oh, one thing I forgot to give you in this. Well, I gave it to you before, but I'll just give it to you here again. This angle, which we denote by gamma, gamma equals convergence, and it's different for every point along our course. And let's see, anything else I want to say about convergence right now? No, I think that's it. We will delve into that more and start learning how to perform more calculations in that environment. So for now, let's talk about coordinate transformation. I have a little spot there. So coordinate transformations. So far, we've been talking about the coordinates of points in terms of their latitude, their longitude, and we've only been using r, the radius, for the height, but that r would be a height value. So in coordinate notation, that would be psi for latitude, lambda for longitude, and r plus h would be our distance. It's the radius of our ellipsoid or sphere or even our geoid, plus our height above or below that surface that is the radius. What we're going to talk about now is Cartesian coordinates. So any set of geodetic coordinates in polar representation, so here, can also be represented. Now we're talking about a point, right? As x, y, and z. And these are called geocentric. Geo meaning Earth, centric meaning center. They're based on the center of the Earth. We're going to use a three-dimensional Cartesian set of axes that are center, whose origin is the center of the Earth. So geocentric coordinates. And this form in our book, as well as any NGS documentation, they refer to as LBH. And that is because, so this is German. What is the notation here? It's in our book. I wrote it down. Lange Breit Ho is what it's called. And that's German. Lange Breit. And make sure I don't forget any umlauts or anything. And Hohe. Hohe, I guess. I don't speak German, so LBH, and that literally means latitude, longitude, height, or close enough that it doesn't matter. And we use LBH because latitude, longitude, height would be confusing because L, same letter, right? So LBH, or geocentric coordinates. And for our coordinate transformation, just a second, let me back up. You'll often see the geocentric coordinate system referred to as ECEF, or Earth-centered, Earth-fixed. Later, we'll get to another coordinate representation called ENU, or easting, northing, up. And we're not going to talk about that yet. It would just confuse the waters, muddy the waters, confuse the situation. We don't need that. So geocentric coordinates or Earth-centered, Earth-fixed. And just to start things off simply, we're all familiar with Cartesian coordinates. So if I have a set of axes, we have our y-axis and our x-axis. So x, y. If I have a point, say, here, and let's say x equals 5, y equals 3, so that 3, and sorry, x is negative 5, then the coordinates of that would be negative 5 and 3, right? Super simple. We've done that since, what, 5th or 6th grade or whatever. Well, we can certainly extend this to 3 dimensions, right? If we were to imagine an axis coming straight at us out of the middle, so an axis coming straight at us here, then we could report that we also have a z component. And this is all review, should be familiar. If this point, negative 5, 3, were to lie on the xy plane, then we could say that it has negative 5, 3, 0 as its 3-dimensional Cartesian coordinates, right? So in a 3-dimensional system, and again, sorry about my drawing, but I'm going to give it a shot. So if we have a set of axes, here's our z-axis, and let's make another axis here, and another axis here. And we could say this is our z-axis. I should be putting little arrows on these, but I'm getting lazy. It takes too much time. And let's say this is our x-axis, and this is our y-axis. It's simpler for me to draw if I start at the xy plane. So let's say there's my x, and let's see. Trying to make these parallel with the axes. Okay. And we can come up then also a z value, right? And here's our point. And that corresponds to our z component here, right? That would have, here's our x value. Let's say that's 5. And our y value, let's say that's 4 units, and our z value. Anyway, z value. And let's say that's, I don't know, 7. 7 units up. I guess that would be better. So our coordinates would of this point would be 5, 4, 7. Well, in Earth-centered, Earth-fixed system, we would have a sphere here centered at the center of our sphere would also be the center of our coordinate system. And that's what's going on with the Earth-centered, that's all that's going on with the Earth-centered, Earth-fixed, or XYZ coordinate system. So that's what we're going to talk about today. Let's explore that a bit. That would be a transformation. So if I can find my, there we go. So here's this familiar diagram. This is the top view of the Earth. So we're looking down on the North Pole. And I'll just write that down. top view. Looking down. Looking down at the North Pole. So the North Pole would be here. And we can see our lines of longitude radiating out from the North Pole. We want to impose an XY system at this point. So our XY coordinate axes. The XY coordinate axes lie on the plane that intersects at the equator. So at the equator, we have, remember, the equator is on a plane that contains the center of the Earth. So any vector radiating from the center of Earth staying on the plane will eventually intersect the equator, right? So let's say we have this point here. And that point, I'll just put a little legend here, that's Greenwich, England. A very important place in London, actually. Greenwich, England. The line of longitude, and there's a line of longitude coming from the pole down the Earth and then hitting the equator and then going back to the South Pole. That line of longitude is 0 degrees, and I'll just say east because we're gonna primarily be working in east longitude. So that's 0 degrees. That's the beginning of our counterclockwise rotation. That's 0, and then it's also 360 degrees, of course, right? Well, if I were to extend that and consider the point on the same 0 degree longitude at the equator and extend a line from that point on the equator to the center of the Earth, that would be our x-axis. Remember, we're looking down on the North Pole. We're looking down at the Earth, and we're just considering this to be the plane of the equator. So if we call this 90 degrees, so this would be the y-axis, or 90 degrees east longitude. And this would be, we come around, this would be 180 degrees east longitude, and then 270 degrees east longitude. No big surprise there, right? Remember, the latitude-longitude coordinate system is counterclockwise. Don't ever forget. I'll probably stop mentioning it at some point, but it's important, right? So we have our x and our y-axis. And here, of course, let's see, if I had a point here, then the x value of that might be 4 million. No, that's not the right number. I don't know what would be a realistic number to pick. Yeah, I guess that would be, it'd probably be closer to 3 million. So a 3 million meter for my x value, and my y value looks like it would also be 3 million. So the xy coordinate would be 3 million, 3 million, and then the z component would be a question mark, right? Now the z-axis is just the spin axis of the Earth, as we would suspect, right? So let's see. I'm trying to find my lateral view. Here's my lateral view. Okay. So this is the lateral view looking. So here's the equator, Here's the pole. And this would be our z-axis. And we can't really see our x and y-axis because we are looking right at the plane, right? So at the x and y-axis just looks like a line. So before we had this point here, and it would have an x value, a y value, and then z here, which conveniently we'll say is 3 million. If it was the same point as our on our last image, that would be 3 million, 3 million, 3 million. And these are in whatever linear unit we want to use. They can be in feet, miles, meters. They're actual measurement units. So the question is, before we get to the question, we know that our point here would also have a latitude, a longitude, and a height. Okay? So the question is, and we would suspect the answer is yes, but is there a function that can take us from any point in one coordinate representation to another coordinate representation of the same point? The answer is, in fact, yes. So let's figure out what that is. So now we need to consider, we need a function. First, let's go the direct. No, let's not do that yet. I'm going to write down a couple of useful useful bullet points about our Earth-centered, Earth-fixed, or XYZ system. So let me erase this. I'll erase all of this. So first of all, we note that the x-axis is along the projection of the 0-degree longitude, or the Greenwich meridian, onto the equatorial plane. And similarly, the y-axis is along the projection of the 90-degree longitude. And I'll put 270 degrees also, right? Because 270 degrees, because I remember axes extend in both directions infinitely. The projection of the 90-degree longitude onto the equatorial plane let's see, the Earth-centered, Earth-fixed, or XYZ grid, I guess, axes, rotate with the Earth. With, I always put E's on the end of my with. The Earth. So that means that no matter what time of day it is, X always coincides with 0 degrees, right? The XY axes lie on the equatorial plane let's see, and the z-axis is coincident with, and you guessed it, the spin axis. A couple of bullet points to keep in mind. Spin axis of the Earth. That will help you in visualizing as we go forward, right? And it's a right-handed system, which means that if my fist is the center of the Earth and my thumb points up the z-axis in the positive direction, the direction that my fingers close is the positive direction, or counterclockwise. That's what a right-handed system means. A left-handed system, if I were to close my hand, then a left-handed system would be positive in a clockwise direction, which is against the rotation of the Earth, right? But we're in a right-handed system, so positive is in the direction of rotation of the Earth, negative is in the reverse direction. Okay, so right-handed system. And I'm going to get rid of all this, and I'm going to bring down the other image. And I think I'll pause it while I go find that other image, so it won't take as long in the lecture. So in order to start considering the transformation from latitude, longitude, all that, to X, Y, and Z components, it's useful to break it into separate perspectives. So the first perspective would be looking laterally. So this is the lateral view. So we're looking at the equator. And let's say we have a point up here. Say there's a, say there's a, I don't know, a mountain up here. There's a mountain, and the point we're considering is on the top of this mountain. So it's not on the surface of the Earth, right? But it still has a line of from the center of the Earth. So if we draw a line from the center of the Earth to that point, that would be, so, and let's say that this distance right here from the point to our model, our spherical model, that distance is h. And then of course the distance here, use a different color, this distance here would be r. So the total distance or radius value that we want to consider is r plus h. So this is r. So let's call this point P. So the distance from center of Earth is r plus h. That makes sense, right? And we have, so I'm just going to make that line. We have everything we need to know to start start forming our z component. So this is the z-axis, and this is the equatorial plane. And we know what this angle is. This is our latitude, right? Psi. And we note that if I were to make some right angle projections to the axes, then r plus h is our radius. What is this right here? What color do I want to use? I'm running out of colors. I'll use pink. If we go from h down to the plane, the equatorial plane, that is our z value. That's our z coordinate. So how do we get that? Well, we have the length of the radius 2 point P from the center of the Earth, right? So that's r plus h, and we have psi. So isn't our z-axis then just a trigonometric function? In fact, isn't this just r plus h? So z equals r plus h, that hypotenuse, times the sine of the latitude of P. That's pretty simple. We can see that right there. Here's sine. This is cosine. So our z component, this is for your notes, our z coordinate is, our z component of the coordinate is z equals r plus h times the sine of the latitude. That's really straightforward, right? So make sure you reproduce this. Okay, had to pause for a second. Technical difficulties, I guess biological difficulties, because dogs are biological creatures. Anyway, they were going nuts over something outside. I don't know what it was. But where was I? Okay. By the way, I started saying before, we're looking at the direct transformation. So the direct transformation we're building a function of the latitude, longitude, and I'll say r plus h to avoid confusion, into x, y, z. So we're developing this piecewise function, right? So we have our z. How do we get our x and our y? I'm going to bring in the other diagram now to work on that. We're going to look at the top-down view. Boom, magic. So this is the lateral view, or the top-down view, top view. So here's the pole in the middle, or the spin axis, right? Because we're really considering just the projection on the equatorial plane. So let's just say this is the equatorial plane. And we have a point, let's say we have a point here. I'll make it less. Let's say we have a point here. That's our P. Okay. Here's our x-axis through the 0-degree longitude, our y-axis through the 90-degree longitude, and we need that value and that value. So we're looking for this distance and this distance. So it would be helpful to know how far from the center of the Earth we are, right? Or the center of the spin, or how far from the spin axis perpendicularly we are. Well, we've done that, right? That's that RP. or the radius of our parallel of latitude, isn't it? And we have RP equals, as we've seen before, is R plus H, or sorry, yeah. Remember, we have a height there, so R plus H times the cosine of the latitude, right? That's just what we had before. So if we knew this angle, then we could get this x value, couldn't we? Well, that angle we know is the longitude. So the x value then becomes the hypotenuse. So x equals the hypotenuse, which is RP, times, where am I? The cosine of the longitude of P, right? If this is the longitude of P, then this distance is just RP times the cosine. So here's the cosine of the longitude times RP. And that's our x value. If I were to expand that, then we have, just substituting this into here, we have x equals R plus H times the cosine of our latitude times the cosine of our longitude. And likewise, I'm going to change colors because I don't like writing in red. Y is equal to that same hypotenuse, so RP, times the sine of the longitude. Pretty simple. That's RP times sine of longitude. That's this here. And that's our y value, isn't it? So if I were to expand that one, then it would also be R plus H times the cosine of our latitude. That's our RP. Times the sine of our longitude. Pretty straightforward. So our set of, I'm just going to scoot this up, our piecewise function then becomes just what we've discovered. So our direct transformation is a function of our latitude, our longitude, and R plus H that takes us to the XYZ coordinate such that x equals R plus H times the cosine of psi times the cosine of the longitude, lambda. Our y is R plus H times the cosine of the latitude times the sine of our longitude. And z equals R plus H times the sine of our latitude. It's helpful to spend some time with this and make sure your understanding is there so that if you need to, you could draw these diagrams and come up with these formula themselves. They're super, super straightforward. So that's how we get from latitude, longitude, and the distance from the center of the Earth to X, Y, Z coordinates. Now, how about the other direction? And like magic, I have a clean slate. So the other direction, we're looking at the inverse transformation. And for that we need a function which takes us from X, Y, and Z to latitude, longitude, and R plus H. And let's say again we have some point P up here on some parallel of latitude, right? Let's look at the longitude first. Longitude of P. So we have this angle here, which is the longitude, right? This is the longitude. And this is our X value, this is our Y value. Well, we're going to use a formula that we've seen before, a trigonometric formula, and that is that the y, or let's see, let me back up a sec. We're looking at longitude, right? It's useful to note that the tangent of the longitude of our point is equal to y over x. That's just straightforward trigonometry. Definition of tangent is the sine over the cosine. And let's see, I got these mixed up, didn't I? You probably already caught that. It would help if I labeled my axes so that I didn't make this mistake, but this is x, this is y, and so this would be our x amount and this would be our y amount here. So the tangent of the lambda is equal to opposite over adjacent, y over x. I've seen that a billion times since 8th grade or whatever. So then we just take the arctangent of both sides. We get lambda of P of our point equals the arctangent of y over x plus whatever constant takes us to the quadrant. Remember, we have quadrants here, 1, 2, 3, and 4. So if our point were over here, we would add C would equal 360 degrees. Here, C equals 0 degrees, C equals 180 degrees, and C equals 180 degrees. Hopefully by now you've reviewed the arctangent and how that works. So this is our first component, which is actually second. So we have this. Let's look at the latitude. So before we move on to the other diagram, it's helpful to note here that our distance from the z-axis, our RP here that we've seen a million times, but remember, we are starting with XYZ coordinates. How do we get the radius of our parallel of latitude with our XYZ coordinates? Well, that's super simple. R sub P is just the old distance formula. It's the square root of x squared plus y squared. Remember, we're starting with our x, y, z coordinates. So we have our x, we have our y, and r sub p is equal to square root of x squared plus y squared. So draw an arrow there, and we'll say that's the square, and we can see that from the diagram, right? X squared plus y squared, right here. That's the length of that guy. The radius of our parallel of latitude given x and y coordinates. So let's grab that other diagram again, the top view. I should come up with a more convenient way of changing these views all the time, right? I'll put it up there. There we go. So here's our lateral view. If this is our lateral view and we have this, our point P here, we have our point P here. We know this is, use yellow, this distance here. Well, we just said that that is the square root of x squared plus y squared. So we know that, right? Well, what are we trying to find? We're trying to find our latitude. So we're trying to find this angle. There we go, and I'll just project our point down to the x-axis. And remember, this distance is the same as above, so that's square root of x squared plus y squared. And what we need is this value here, right? How high this our point P is above the equator. Well, don't we know that? P. Isn't this the z-axis? Remember, this is the lateral view, so this is just the z value here. So then our psi becomes the arctangent of the z value of our point, I guess I should do that, over x squared plus y squared. There we go. And that's our psi. And that follows directly from the image there and what we built. The tangent of psi would be z sub p over the square root of x squared plus y squared. Take the arctangent of both sides. And then, of course, we have to, I probably shouldn't have boxed that yet. Say plus c, where we adjust for quadrant. And over here, it was c equals 0 degrees again. Over here, c equals 360 degrees, etc., etc. Okay, where does that leave us? We now have, so remember, we're trying to get a function that takes us from x, y, and z to latitude, longitude, and r plus h. And even sometimes we'll just see this because r is defined. Whether it's an ellipsoid or a sphere, r is defined as the definition, straight from the definition of our mathematical model. So we might see this. We often do in the LBH system. So instead of r plus h, just h. And we can find both, can't we? So let's see, what is the r plus h? Well, right here, that's this. This is r plus h. So r plus h equals, well, that's just another distance formula. Super easy. X squared plus y squared plus z squared. Because remember, our line here is extending from the center of the Earth, right? And so that's just the definition of a vector, or that's how we find the length of a vector from the origin to a point. It's just the distance formula. So from that, we could also say h equals the square root of, and this is just basic algebra, plus y squared plus z squared minus r. All I did was move the r over to the other side. Okay, so here is this way. All right, let me summarize. Summary. The function that takes us from, which way did we go first? We went psi, that's a psi, lambda, r plus h, to xyz is x equals r plus h times the cosine of psi times the cosine of lambda y is equal to r plus h times the cosine of psi times the sine of the longitude, and z equals r plus h times the sine of the latitude. Okay, we derived those. That is the direct transformation and then going the other way, scoot this up just a little bit. Going the other way, we need a function that takes us from x, y, z, it's a piecewise function, into psi lambda r plus h, or psi lambda h, and that goes like this. Okay, so start with the latitude is equal to the arctan of z over x squared plus y squared plus some adjustment for the quadrant, and lambda is equal to the arctan of y over x, and we adjust for quadrant, so plus c, and then h equals the square root of x squared plus y squared plus z squared minus whatever the definition of the mathematical model the radius at that point is. And that is the inverse transformation. So now, this is powerful. We have a way of going from familiar XYZ coordinates, which adhere to Cartesian and Euclidean principles. We can go from that grid system to a latitude, longitude, and height. And we know how to go back. So we'll explore some of that more as we go forward. It gets a little more complicated as we go to the ellipsoid, of course, but transforming between geodetic coordinates and Cartesian coordinates really is not that complicated. If you ever forget these, you can just draw the diagram, draw your circles, and rederive them. Okay? So I'm going to leave that for here. Again, sorry it's another long lecture, but I think that expanding on these ideas and maybe giving a little too much information is better than not giving enough information. Hopefully I'm clearing up confusion as I go. But as always, if I've confused you, please give me a call or an email or a text and we can set up some Zoom time, all right? So with that, have a good rest of your day and I will talk to you later.